Hello and welcome to iitiansgateclasses once again. So today we are starting with the address calculations of array 1D array, 2D array, and these kind of questions asked in many programming interviews, or you can say many examination, mainly in examinations. So they give you address and they will give you the starting index of the address, the base address, and array could be 1D array, 2D array, 3D array will be more complicated, but it will follow the same pattern. If you want to find out address of the 3D array, it will follow exactly the same pattern. Okay, so let's start ahead and start with the 1D array address calculation. So let's assume a array of array is given like this, having 10 elements. Okay, starting from 10, 20, 30, 40, 50 till 100. Okay, so these are the elements like 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Now let's assume that the base address I will indicate as B. Base address is 1000. So it's an integer array, and we will consider the size of integer array to be 2 bytes. It's given that each element of integer array is taking 2 bytes. Okay, so how can I represent this in a memory? We have address, we have an array A. It will be stored like 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. And the starting address, I will try to write the addresses in green color. It's 1000 here, 1002, 1004, 1006, 1008, 1010, 12, 14, and here we have 16 and 18. Okay, so these are the addresses. Now if somebody asks you what is the location of A7, so if the array is given like this, right? Array is given like this, and they ask you the location of the A7. It is simpler. You can, it is very simple. Like you can write the array and you can find out the address. But there may be some complication here. I will tell you later on in the lecture. I will give you some more complex addresses. Okay, so we have to define a formula here. Okay, so the formula is basically, we will consider the base address, which is 1000 here. And we will see that, okay, this is the index that they have given, A7. We have to find out 7th index address. So you will say that 7. And then you will consider the starting address, the starting index. The starting index is 0. If they have given you A0, you can simply tell it's 1000. Okay, the address of A0 is 1000. A0 is not 1000. Address of A0 is 1000. Then 7 minus the starting element address multiply by the size of each element. Size of each element is 2. Okay, size of each element is 2. So the address will be 1000 plus 7 minus 14. 7 minus 0 is 7, multiplied by 2 equal to 14. It will be 1014. So you can say that 0, 1, 2, 3, 4, 5, 6, and 7. See, the 7th element address is 1014. Now, what if they tell you that instead of starting it from 0th index, start it from, I am starting from index 2. Okay, I'm saying that my array is actually starting from index number 2. Okay, I'm just assuming. Sometimes they give you like this, okay, that the index of the first element is 2, not the address, index. It's 2, then 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, my array is ranging from index number 2 to 11. It is given in the question. Okay, then what is the address of A7 here? Okay, what is the address of A7 here? Now remember the previous formula we have applied. What we have done starting address, which is 1000, plus the index that we want to find out, which is 7, minus starting element, the first element index, which is 2, multiplied by size of each element, which is 2 bytes here. Okay, so it's 1000 plus 5 multiplied by 2, and the answer is 1010. Now see, 7th element address is 1010. That is why this formula is required. Sometimes they can give you address instead of 2 or 0, they can say that, okay, it's starting from -2. Okay, it's starting from -2. Let's try to find out the index of A7, where we are starting from -2. Then the address of this index of this element is -1, 0, 1, 2, 3, 4, 5, 6, and 7. Then what is the address of A7? Address. We are calculating address, not the element, right? So address is the base address, which is 1000, plus element, the index of the element which we of which we are trying to find out the address, which is 7, starting 1 minus -2. Okay, multiply it by size of each element, which is 2. So it's 1000 plus 7 plus 2. Minus is plus, right? 1000 plus 9 multiplied by 2, which is 1018. See, A7 is 1018. So this is how you can find out the address of each element in 1D array. Okay. Now, once we move on to 2D array, first, before moving on to 2D array, let's see what we can conclude using this thing, right? So this is how computer also calculate the address of each element, each index, you can say. Once you pass something like this, what it do? It will say that, okay, base address. What is the address of first element? Okay. Sorry. Base address plus like 6. The index of the element which you for which you are trying to find out the address, 6, minus starting address. So we can indicate as LB. Okay, starting index, not address, starting element index. Okay, starting element index. So this is LB, multiply by size of each element, This is the general formula. Okay. Now, if we start from 0, if we assume that array address, array index, not address. So don't get confused between address and index. These are the address which actually saved in the memory, and these are the indexes. Okay, so assume that index of first element is always 0. Then what is the benefit of it? What is the benefit? Why we didn't take it as 1? Okay, you can see the benefit right now. Put 0 here. Okay, in the formula, put 0 here. So we have now base address plus 6 multiplied by size of A6, right? So we are actually saving one operation, the subtraction operation. That is why in array, we always consider the base index of first element as 0. So that further, whenever we want to find out the address of any other index, for example, here we are trying to find out address of 6th index element. It is easy for us. The subtraction, like 6 minus 0 is 0, right? 6 minus 0 is 6. 6 minus 0 is 6, right? So that is why this operation is not getting performed. We are saving that one computation for each address calculation. So that is a huge benefit. Now let's move on to the another example where we are going to take 2D array. Okay, 2D array. I will show you what is column measure and row measure. In 1D array, it doesn't matter. It's not column and row measure are like not relevant, but in 2D array, it's relevant. So let's move on to 2D array. Okay, 2D array. 2D array means we have rows and columns, okay, of any size. It is possible. Okay, so let's assume that here the starting address of each starting index is 1. Okay, starting index is 1. So if we have an array of 5, 4, array A54 means we have 5 rows in total. I'm saying that this is the maximum size. Okay, we have 5 rows, 4 columns. Okay, so I'm going to write all the elements here. Like we are starting from 1 first. Okay, so we have 4 columns, 1, 2, 3, and 4. We have 5 rows, 1, 2, 3, 4, and 5. So our first element will be A11. Okay. Second element will be A12. I'm just indicating as a variable. So A12 means first row, second column. A13. First row, third column. A14. First row, fourth column. Similarly, second row, first column. Second row, second column. Second row, third column. Second row, fourth column. Okay, this is how I am going to write all the element indexes. All the element indexes. Okay, 3, 2, 3, 3, 3, 4, A41, A42, A43, A44, 53, A54. Okay, so these are the elements because I started with 1 first index, the starting index as 1. That is why it's A11. If I start with 0, it will be A00. Okay. Now, how do I find out number of rows if I have given something like this? Number of rows I want to find out. Okay. Remember this. Okay. See, the thing is, this is important. Right now, we are starting with 1. Later on, we will also start with some minus indexes similar to the 1D array we have calculated the address. Okay. We can start with minus indexes. Okay. Negative indexes. Here we can pass -2 or -55. In that case, calculating number of rows or number of columns are important. Okay, here, remember the number of rows can be calculated as, look at the last index and look at the first index. 5 minus 1 plus 1. These are the number of rows we have. Number of rows, what is the meaning of number of rows? Number of rows means, write this down. Number of rows means total element in each column. Okay, total element in each column, or you can say number of element in each column. That is the meaning of number of rows. Count it like, okay, it's 5 minus 1 plus 1 is equal to 5. So we have 1, 2, 3, 4, 5. 5 element in the first column. In the second column, 1, 2, 3, 4, 5. Okay, 5 elements in each column. We will have 5 elements. So number of rows are basically, number of rows means number of elements in each column. That's what it means. So it will be helpful for us to identify address of given indexes. Okay, and number of columns. Here, what is the number of column? It's 4 minus 1. This is the last column. This is the first column index. 4 minus 1 plus 1. So it is 4. Number of columns means number of element in each row. Okay, in each row. So here it's 4, right? At each row we have 1, 2, 3, 4, 1, 2, 3, 4, 4 elements. Okay. I hope this is clear. It's quite simple. Now, what is row measure? What is row measure? So, what is row measure? Row measure order. It is row measure order, in which we calculate the address like row wise. First, we will give address to it. The next address we will assign to this element. The next address we will assign to this element. Then this element. Then we will move on to the next row and we assign next address to this one. Okay. So how elements will be stored in the memory? They will be stored like this. Okay. Remember these indexes, A11, 12, 13, 14. So they will be stored like this. Okay. They will be stored like this: A11, A12, A13, A14. Then we will move on to the next column, next row, sorry. So because it's row major, we are going row by row. Okay, the next row, which is A21, A22, A23, A24. The next row, A31, A33, A32, A33, A34, A41, 42, 42, 43, 44. Then A51, A52, A53, A54. Okay, this is how they are going to store in the memory. Now you can see the address. For example, its address is 1000. Then the next address will be 1002, 1003, 1004, 1008. Sorry, no, 23. After, sorry, by mistake, I have written 3. It's actually 1004 because size of each element is 2 bytes. So it will be 1004 here, 1006, 1008. Then 1010, 1012, 1014, 16, 18, 20, 22. Here it will be 24, 1000. Okay, I'm not writing 1000 now because of space. It's 24, 26, 28, 30, 32, 34, 36, and 38. Okay, so these are the addresses. These are the addresses. Now, if I want to find out the address of A31, for example, I want to find out address of A31. What is A31? A31, you can say it's A31. Okay, what is A31? This is A31. We know its address because we have written its address. Because it's a small 2D array, okay? Only contains 5 rows and 4 columns. As it's row major order means this is first row. After that, we will have second row. After that, we will have third row. It will be stored like this, okay? Stored like this. These are rows, first, second, third, fourth, and fifth. These are the rows. This is how they are going to store in the memory. Okay, what is the address of A31? So we will say that, okay, what is the base address? Base address is 1000. Write this down. How many rows do we have already calculated before the third row? How many rows do we have? It's actually 2 rows we need to skip. To calculate the address of A31, we need to skip 2 rows before it, 2 rows. Okay. 2 rows we need to skip, right? And what is the element number in this current row? It is the first element. It is first element, right? First element. So we need to skip 2 rows. We need to skip 2 rows. And in these 2 rows, we have how many elements? We have 4 elements each. So these many elements we have to skip before A31. And what will be the address of, or you can say, what is the position of A31 in third row? In third row, what is the position? It's the first position. So for first position, we will say that, okay, let's write 1 here. So, sorry, 0 here. These many elements we need to skip. And this is the element that we want to address in the third row. And once we multiply it with this size, we will have how much? 1016. Let me formulate it. It will be easier for you. Let me formulate it. So we are going to say in row order, we want to find out location of A31. As per these indexes, where we started from 1, okay, where we started from 1, not 0. So we say that, okay, let's consider base address, which is 1000. Base address plus Okay, it will confuse you. This B bracket 1000 may confuse you. So I will write down the base address. We have considered the base address as 1000. So we write 1000 here. How many rows are we going to skip? 3 minus 1. 3 minus 1. We are looking at third row. We are looking at third row. Okay. This 3 is saying that we are looking at row with label 3. And if we want to find out how many rows did we skip, 3 minus starting row. Starting row. So it will be 3 minus 1. And how many elements do each row have? 4 elements. Each row is having 4 elements. What is the column position of this element? It's 1. Minus. What is the starting of this column? Starting of this column is also, starting of this column is 1. Starting of the column is 1. Multiply with size. Okay, so this is 1000 plus 2 multiplied by 4 plus 0 multiplied by 2. So it is 1016. So let's give a generic formula to it. The generic formula is its base address plus for location, we are finding out location of aij. Okay. For aij, it's base location plus I minus starting address of starting index of the row. Starting index of the row. LB means base. LB1 means starting index of the row. The starting index of the row. Multiply by UB2 minus LB2 plus 1 plus J minus LB2. Okay. Multiply by size. Now, what is it? What is it? It's number of row, number of elements. So this LB means actually lower bound. UB means upper bound. Okay. So this formula may confuse you. Let me write down all the definition here. LB once means low bound of row. UB1 means upper bound of row. LB2 means lower bound of columns. COLU columns. And UB2 means upper bound of columns. So don't try to mug up the formula. You will forget it in the examination. Instead of mugging up the formula, try to remember that once we are in row major order, what are we achieving? To identify the position. We are trying to find out that before the current row, how many elements did we skip? Before the current row, how many elements did we skip? Okay. So we are actually, this 3 is indicating that we are at the third row. Third row with the label 3. Okay. So before it, how many rows did we skip? We skipped 3 minus 1 rows. 3 minus 1. Why 1? Because the starting row start with 1, not 0 or not anything else. So these many rows we skipped. We multiplied with elements in each column. So in each row, elements in each row. And elements in each row, how can you identify number of column, or you can say that see, number of rows are total elements in each column. So You want to find out number of elements in each row. So you have to identify number of columns, right? So number of columns, yeah. So how can I identify number of columns? It's 4 minus 1 plus 1, right? I have given you the formula, 4 minus 1 plus 1. This is the upper bound of the column. This is the lower bound of the column. This is the upper bound of the column. This is the lower bound of column. So we have denoted the upper bound and lower bound of the column as this thing. So it's UB2 minus LB2 plus 1. So this is the number of element in each row. Okay. Using this formula, we can identify number of element in each row. And how can we identify number of element in each column? It's UB1 minus LB1 plus 1. So this is basically number of elements in each column. Okay. Okay. So using the upper and lower bound of the column, we can identify number of elements in each row. Okay. So what we are doing for 3-1, we are trying to identify number of elements we skipped to reach third row. Okay. Number of elements to skip to reach third row. So how many rows did we skip? I minus LB1. I minus LB1, number of rows we already skipped. And in each row of that skipped rows, we have these many elements. Okay. Number of elements in each row. We have these many elements in each row. Okay. Now we are identifying, we have reached to the third ith row. We have reached to the ith row. Now what is the position of our element in the ith row? Jth position we have, jth position. And J in compared to what? LB2. Okay. So lower bound 2 indicates the starting of the column. This is LB2. Okay. This is LB2. This is UB2. This is LB1. This is UB1. So if you want to identify this element, for example, how many elements did you skip to reach to 3, 3? You actually skipped. Look at this 3. 3 minus, look at LB2. LB2 is 1. 3 minus 1. These many elements you skipped. So you skipped 2 elements. Let me take another example for you, and it will be easier for you to understand this formula. Let me try to write this formula again. So remember this thing. Number of element in each row is basically UB2 minus LB2. UB2 minus LB2 plus 1. Okay, upper bound of the column minus lower bound of the column plus 1. These many elements we have in the row. So this is number of elements in each row. Okay. Okay. So that is why the formula is basically base address ij, base address plus I minus LB1. Okay, these many rows we have skipped. Number of rows we have skipped. Or you can say before current row. These many rows we have before ith row. We could start with minus 50th row. We can say that our first row index is minus 50. So in that case, if I is equal to 2, how many rows did we skip? We start from minus 50, then minus 49, then minus 48, minus 47, 0, 1, 2. So how many rows did we skip? We skipped 2 minus 50, which is 52 rows we have skipped. 52. If you count these things, minus 50 to 1, these are the total 52 rows we have skipped. In each row, how many elements do we have? We have these many elements. UB2 minus LB2 plus 1. These many elements we have in each row. Now, once we reach to the current row, which is ith row, we try to look for the current position in the row. So the position in the current row is this column, J column. Jth is the column of the position in the current row. Okay. So this position, we can say that J minus LB2. Okay. This is the position of the element in current column. Multiply it with size of each element. This is the address. I hope you understood it. Let's take some examples here and try to solve this. Okay, let's take a very typical example where it is given that our rows are indexed from minus 55 to plus 55. Okay, sorry, to plus 55. These are the index of our row, and our columns are indexed from plus 55 to 155, plus 155. This is how our indexes are given. Now, our base address is 999. Size of each element is C equal to, let's assume that the size of each element is denoted by C. C is equal to 3. Now it is asked to give us the location of element A50, A120, A120. Okay. What is the location of A50 by A120? Let's see. The formula is base address is 999 plus the number of rows we skipped to reach 50. To reach 50th row, if our which is 50 minus 55. These many rows we have to skip. Then we have to calculate number of element in each row. Number of element in each row, which is this is what UB2, this is what LB2, this is LB1, this is UB1. Okay. So how many elements do we need to skip for these many rows? It's UB2 minus LB2 plus 1, which is 155 minus 55 plus 1. Okay. Okay. Then we do that. Okay. These many elements we skip to reach current row. Now in the current row, our position is 120, but our starting position is not 0, it's 55. Okay. So what is our current position? How many elements do we need to skip in the current row? It's 120 minus 55 elements we have to skip. Okay, this is the starting braces, this is the ending braces. Multiply with size of each element given as 3 bytes. So this will give us the address. So let me write the answer. It will be 33,009. This is the answer. I hope it is clear now. Similar to this, if we understand the row measure, to understand the column measure, it will be easier for you to understand column measure. Okay, let's write down column measure order. Column measure order. We are going to consider the same this 2D array. Now let's see how are we going to write this in the memory. in which order? We are going to write it like this: A11, A21, A31, A41, 41, A51, then A21, not A21, A12. This is the first column we have. Okay, this is first column. This is how they are going to be written in memory sequentially. First, we are going to write the first column, then the second column. Okay, then the second column. Second column starts from A12, A22, A32, A42, A52. Then the third column, A13, A23, A33, A43, A53. Then the fourth column, A14, A24, A34, A44, A54. Okay. Now to reach to index ij, remember what is, write this down, keep it handy. LB1 is lower bound index of the row. UB1 is upper bound index of the row. LB2 is lower bound index of the column. UB2 is upper bound of the column. Now, how can we write number of element in each row, which is UB2 minus LB2 plus 1. Number of element in each column, UB1 minus LB1 plus 1. Okay. I have already given you the example. Like here, if I want to find out number of element in each column, it is UB1 5, LB1 1. 5 minus 1 plus 1, which is 5. So we have 5 elements in each column. Okay. So let's move on to our target, which is find out the location of iij. So let's give us the generic formula. It is same as the previous one. Just we need to swap few variables. Base address means address of first element, plus to reach to jth column, how many columns do we need to skip? If our starting column address is LB2, these many columns we have to skip. And how many elements in each column do we have? We have UB1 minus LB1 plus 1 elements in each column we have. Okay. Once we reach to jth column, what is the position of ith element? Okay. So we are starting from like LB1, then we go to some like LB1 is the first, the index of the row. Then we will go till ith element. Because right now we are scanning element like this. First this column, then the next column, then this column, then the next column like this, right? We are going like this. See, A11, A21, A31, A41, A51, okay? So you can see here, it's A11, A21, A31, A41, A51. Then we will go like this, okay? So to reach to this element, we have to skip how many columns? These many columns, okay? 4, like this is the 4, this is J, right? J. 4 minus 1. Minus 1 means LB2, okay? 4 minus 1, J minus LB2. J minus LB2 columns we have to skip. And each column, how many elements do we have? 5 minus 1 plus 1, which is UB1 minus LB1 plus 1 elements we have in each column. Now, once we reach to our column, how many elements do we have to skip to reach A24? 2 minus LB1. 2 minus LB1. Okay. So it's J minus LB1. So not J, it's I. I minus LB1 elements we have to skip in the current column to reach to our element. Multiply by C. C is the size of each element. Okay. So this is the formula for column measure order, right? Now they may ask one tricky question. Okay, so in row measure order, they may ask you one tricky question that they can give you a array where row are starting from 1 and going till 4, column are starting from 1 and going till 4, and we have a 2D array like this: A11, 0, 0, 0, A21, A22, 0, 0, A31, A32, A33, 0, A41, A42, A43, A44, like this. Now this is called lower triangular matrix. Lower triangular matrix C. Only the lower triangle have the elements. Okay. So how can we count number of elements we have? We have one element here, two elements here, 3 element here, 4 element here. Okay, it's increasing in each row. So if we do 1 plus 2 plus 3 plus 4 till n, where we have n rows we are having. How many elements do we have? N plus 1 by 2. These many elements we are having in the lower triangle. Now they may ask you, give us the index of A43. It's very easy. This is our base address, right? This is, consider this is our base address. Then how many total elements can we have before, you can say, before fourth row? We can have 3 into 3 plus 1 divided by 2 elements. Okay, these many elements we can have. The answer of 3 plus 1 divided by 2 is actually 6. Okay, so till 3, how many elements can we have? 1, 2, 3, 4, 5, 6, right? If we are finding the address at 4th row, we have to skip all the, or we have to consider all the elements before 3rd row. So how many elements do we have before 3rd row or before 4th row? How many elements do we have before 4th row? It's 3 plus 1 divided by 2. Very simple, right? Then you can add the position of current element, which is 3 minus LB2. What is LB2? 3 minus 1. It's actually 3 minus 1. Okay, multiplied by 2. 2 is size of each element. We are considering size of each element is 2. So this is the formula for, in row measure order, this is the formula. In row measure order, this is the formula. Okay, quite easy, right? So what we did here, actually we calculated that before reaching to the current row, how many elements do we need to skip? Right? If our row is fourth row, if our row is 4, we have skipped 3 rows. If we start from 1 and going till 4, if our current row is 4th row, we have skipped 1st row, 2nd row, and 3rd row. And how many elements do we have in the 1st, 2nd, and 3rd row? 3 plus 1 by 2. Then let's only take the headache of the current row. In the current row, our position is 3. So how many elements did we skip? 3 minus 1. 3 minus 1. Why 1? Because our columns are starting from 1. And let's multiply it with our size of each. So I hope you understand how we are proceeding with the addresses. Okay. So before going to the current row, in the row measure, we always calculated how many elements, how many rows did we skip. Then we multiply it with by how many elements each row contains. Okay. Then we add the current number of elements we skipped in the current row. Okay. The number of elements we skipped in the current row. Okay, these are the elements. These are the elements that we skipped before current row element. So this is the position of column in the current row, and we multiply it with size. Okay, and we are good to go. So this is how, similarly, you can also calculate column measure in the lower triangular. Is the same thing. So this is, nobody will ask you a more difficult question in the calculation of address of each row, each any element given, any indexes of a 2D array given, and they ask you they have given you the base address, and they ask you the address of a given index element address. It will be easier for you, right? If you approach like this. Okay. Now let's move on to our next topic, which is structure and union. I will give you some very basic understanding of structure and union. Okay. Then we can go ahead with some more complex structure, or you can say applications of structure and union, which is linked list and trees. Okay. So what is a structure? It is a user-defined data type. User-defined data type. Okay. So previously, the array we have looked, and we have looked at primitive data type like integer, character. We have seen that how integers are saved in the memory. So the structure and union. So we can define a structure like struct, struct. Okay, struct node. Then you can give a bunch of data types here, like int, a, float. Float means which can contain fractional values, 2.3, 2.5, 7.6, something like that. Character, C. Okay, we defined a data type like this. So in case, what is the difference between structure and union? Somebody can ask you like this also. So this contains 2 bytes. Consider this as a 4 bytes, and this as 1 byte. So we have 7 bytes. So structure generally take the whole data types, calculate its size, and try to save it in that memory. Okay. So we can define structure like this, and we can assign value like struct node d equal to 10 curly braces 10, 20.5, g, something like this, right? So it will create a variable type d. It will create a variable d of type struct node structure, and it will save values 10 into a, b, and 2.5 into b, and g in c. So if you want to access any ABC, how can you access? You can say access like d dot a. D dot a. It will give you value 10. If you do d dot c, it will give you value g. Okay, this is how you can define structure. Now in union generally takes whichever is the biggest out of these 3, 4 bytes. It will allocate 4 bytes to the node. It will allocate 4 bytes. That is the difference between structure and union. In structure, it will define the whole memory, like 2 plus 4 plus 1, right? It will define 7 bytes. Union will define a memory of 4 bytes. Okay. So now let's move on to our next application of structure, which is linked list. So we can define, we are capable of defining linked list right now. What is linked list? Some people are very scared of linked list. I don't know why, but it is very easy. What is a linked list? Linked list can be defined a very simple node of a linked list. Linked list are collection of nodes, right? Like we have node 1, like this. It is connected to node 2, and it is connected to node 3, and it can keep on going until the last node. Okay, what is this connection here? In programming language, what is this connection? Once we understand the structure, okay, let's define a structure again. Struct node. Here, somebody very smart person have done like this: int data. Then that guy have done that instead of giving some other data type, let's try to give a data type like struct of this type only, struct node only, self-referring pointer. Next. So generally this will be of 2 byte and this will be of 8 byte. Generally speaking, I'm saying, if somebody tell you that we are going to store integer in 4 byte in the examination, that's okay. But right now what's happening? Look here. This is a single node. This is a single node definition, not a node. Till now we haven't created any node. It's just the definition. That this is an integer type data we are going to store, and in the another data type of the structure node, we are going to store a pointer to another node, of same type. Same type means struct node type. Now somebody can create using this definition. Int data struct node star next. So this is the definition of the node, right? Now I'm initializing several nodes here. I'm going to create several nodes here, like struct node a equal to 10 comma null. Right now I'm storing null in this pointer. Okay, I'm creating several nodes. This is the using this definition, struct node b equal to 20 comma null. Struct node d or you can say c equal to 30 comma null. Struct node d equal to 40 comma null. Okay, so I have created 4 nodes. Right now there is no connection between them. Once I say that a dot, okay, what if I print a dot next? What it will print? It will print null. Okay, it will print null. But what I can store in a dot next? The type struct node pointer we can store in the a dot next. Okay, so if I do a dot next equal to, if I do something like this, a dot next equal to and %b, it will pick the location of starting location of the b and save in a pointer a dot next. Save in a pointer a dot next. So I can do this also, b dot next equal to and %c, and c dot next equal to and %d. How can we visualize it? We can visualize it like this. We have a node A in which we have a integer 10 and a pointer, a location. Here we have a location. We have a location here. Okay, let's see that we have a location. Let's see the location. Right now it has some location 2000. And the starting address of this node is basically some 1000. Okay, and it have a location 2000. Now we created a node B. It have value 20 and it have a location 2000. Initially it will create it like this. Okay, let's start from the beginning. Once we run only these lines, it will have something like null here, null here. Then it will create a node C of value what? 30, null here. D also 40, null here. After executing these lines, it will create 4 nodes A, B, C, D. Okay. And what is the address of C? Let's assume that it's 3000. The address of starting address of C is 3000. The starting address of D is 4000. This is what it did. Okay. Once you execute this line, A dot next equal to and %B. And %B is what? 2000 is the and %B. It assigned and %B in the place of next. This is next, right? This is next. So it will assign it in here. It will replace null with 2000. Similarly, it will replace this null and this null also. Once you execute this line, it will replace this null here with 3000. And once you execute this line, it will replace this null here with 4000. Okay. So this is how a linked list is created. Now this is a linked list. This is a linked list. Okay. So we have a 4 node. We have 4 node A, 10 with some address in it, like 2000. B, and we have 20, and we have some address in it, like 3000. C, 30. We have address 4000, and we have one more node D with 40 value and null here. Null here, right? The starting address of A is 1000. The starting address of B is 2000, which is stored here. The starting address of C is 3000, which is stored here. The starting address of D is 4000, which is stored here. Once we execute this whole program till here, it will create 4 nodes and allocate addresses like this. So this is a linked list. So instead of writing the starting address here and again address here, in short, for better visualization, we write it like this: A10 and this arrow B. This arrow is saying that the address of B is stored in the next pointer of A. In the next pointer of A, right? 30 C, 40 D. And here we have null, nothing. So there is no arrow, right? There is no arrow means here in the next pointer there is a null, which indicates end of the linked list, end of the linked list. Okay. So now if I want to have this linked list, what do I need? I only need address of A. I will have a start pointer of type struct node. Struct node type, I will have a start pointer. Struct node start star, and I will say and %A. Okay. Once I write like this, what did I write? Okay, it's a bit messy. Let me write it again. Struct node start equal to and %A. What does it say? It says that I have a structure pointer start. It means I have whole linked list. How can I access the whole linked list? I can access the whole linked list as if I say that, okay, start arrow data. It will give me 10. The value of, once I print this value, it will give me 10. If I say that start arrow, why am I doing arrow, not dot? Because dot is not for the structure pointer. This is structure pointer. So in C programming, we have to do the arrow. If we are using structure pointer, we have to do the arrow. It will give us value 10. If I do start dot next, it means that it will give me next structure pointer, the next node in the linked list, this node. So if I print start arrow next, arrow data. I will print 20. So this is how I can go. I can go like start, next, next. Now I am at, this is second node, this is third node. I am at third node right now. Once I print data here, it will give me 30. So this is how a linked list can be accessed. Now you can apply loop on them, while loop, for loop, something like this, right? You can iterate the linked list also. Actually, in memory, it will be saved like this. But for the ease of use, for better visualization, for better understanding, to write better program, we generally write them like this. Okay, A will have 10 value, arrow B. It means that the starting address of B will be stored in the next pointer of B here. Here it will be stored. Okay. Thank you all for joining. And tomorrow we will start looking some linked list programs. Some very good questions on the linked list also. Thank you.